Andre. As a matter of fact, we're starting the recording. All right. So we're going to do another application in section 3.3 where we need to use MATLAB code. And of course, the MATLAB code is pretty simple that for these problems. If you just look at the code and sort of piece things together, you can get a pretty good feel of why the commands have this value or that value. But certainly, always you can see me if you have questions on it. But let's go ahead and look at this this situation here. So here, a radioactive series. Okay, so this is an important application for modeling with a system of first-order differential equations. Okay, so when a substance decays by radioactivity, it usually does, I'm just reading here, when a substance decays by radioactivity, it usually doesn't just transmute in one step into a stable substance. Rather, the first substance decays into another substance, which in turn decays into a third substance, and so on. The process, called a radioactive decay series, continues until a stable element is reached. How many have heard of radioactive decay series maybe in chemistry class? Like X going to Y, going to Z. Okay, Anne's heard of that, and Thomas has. Yes. And so you have these decay rates. So X decays like in the, let me just see here, hold on. One moment. So like for instance, X decays to Y at the decay rate of negative lambda 0.1. Y decays to Z at the decay rate of negative lambda 0.2. Okay, and those are your decay constants. So you can represent, for instance, the decay of element X with respect to T as negative lambda 1 times X. The lambdas are positive. So that differential equation represents what kind of decay? You should know this. Hold on, is it showing here in the thing? Hold on. No, let me bring it back. All right. Okay. Okay, so again, radioactive decay series. We're taking a simple case where X decays to Y, Y decays to Z at decay rates negative lambda 1, negative lambda 2. Well, we can describe for a radioactive series a set of differential equations, a system of first-order differential equations. So the decay rate, well, dx dt equals negative lambda 1 times X. Let's look at that first differential equation. That's saying that element X is decaying how? How would you describe the decay of this radioactive element X? Is it logarithmic decay? No, it's not logarithmic decay. It is, we don't even know what that is, right? Good, Michael. Exponential decay. Good, very good. All right, so X decays to Y. But now look at dy dt. dy dt equals positive lambda 1x minus lambda 2y. Now what's going on there? Why is dy dt equal, why do we have a positive lambda 1x there? Why would that be?
Is it because it's being created from X?
That's right, Antonio. Very good. Very good. Y is being created from X. So the atoms that X gives up go to Y at the same rate, lambda 1x. However, what's happening to Y? Simultaneously, Y is turning into what element? Decaying into what element? Good, Ann. Y is decaying into element Z, element Z. So you have to then say, okay, minus lambda 2y. So y is exponentially decaying into, I mean, at the same time it's gaining atoms, it's losing atoms to y. And that's why you have that. Okay, and then finally, what's going on with z here? dz dt equals lambda 2 times y. Now, does that represent exponential growth or exponential decay? That's right, Antonio, growth. It represents growth. And that makes sense because the Z is the end. It's the stable product. That's right. So you end up with Z. That's right. And so we have a system here of first order differential equations. And we can use, well, obviously, if we're presented with these three differential equations, and of course, lambda 1, lambda 2, and lambda, sorry, hold on, one moment here. One moment. Yeah, lambda 1 and lambda 2 are going to vary depending on what element you're using, but we can use a program in MATLAB. I actually wrote it, but I get a little help. I look on the internet and learn how to do things. But there's a program in Blackboard that will graph solutions for X, Y, and Z to tell you what is how many grams of the substance are left and so forth. So what I want to do here, let me just first of all go right to an example here. I'm going to just pull it, I'm going to get it right from the book. Hold on here. Let's see, it's in the exercises, so I'm looking for the exercises. Here we go. So it's the second problem, okay, and they give decay constants K1 and K2, and initially you have 20 grams of X. Use a graphing utility. So that, here's the whole problem. Use a graphing utility to obtain the graphs for X, Y, and Z, and use the graphs to approximate half-lives of substances X and Y. Now, incidentally, what is a half-life of a substance? What's half-life mean?
It's the time to decay to half the original value.
That's right. It's the time it takes. If you start off with a certain amount, how long does it take for that amount to decay to half that amount? That's right, Michael. That's right. So the MATLAB program for this goes with this particular problem, okay, and there are those constants K1 and K2. But of course you can adapt it because in WebAssign you'll have different constants. So let's take a look here. Let's take a look at the solution to this problem. So what we do here. Let me just find the program. So everything's being recorded, of course. Okay, so all right, we go to MATLAB programs. Click here to see the MATLAB programs, and here it is, 3.3. Now, you already worked with one MATLAB program in 3.3, but this second MATLAB program will help you graph solution curves for radioactive series. So you just click on the MATLAB program, okay, and then it should open in your hold on. MATLAB. So give me just one moment here. Okay, good. So let me go into the MATLAB and make it visible here. Okay, so here's the code. Here's the code. And you notice at the beginning of the code, I have clear vars. Clear vars clears out the variables in your workspace. And I'm going to graph 3 plots. Of course, I'm going to calculate values of the solutions numerically using ODE45 again. That's the Euler's method program for MATLAB. And I'm going to create a plot for the X, the Y, and the Z. But after I create the plot for the element X, I do a hold on. Hold on means that I want to, like it means hold that graph, MATLAB. I'm adding another graph. And then I'm going to add a graph for the solution points for element Y, and then the solution points for element Z. And then I say hold off. Hold off means, okay, now produce the graph. We're not going to add any more, curves to the graph. So we should see a graph with, when we run this, we should see a graph with 3 curves. So I'm going to do a select all. I'm going to do a copy. Okay. I'm going to paste it in the command line. Paste it in the command line and hit enter. And now, if you go to your figure, there should be a figure produced. All right. Are there any questions so far? All right. Let me go to the figure. Here's the figure. Okay. There's the figure. Now I purposely did not. I could have made my t-axis longer. Okay, I could have done that, but there are 3 curves. There's a blue, a red, and a yellow. And I purposely didn't label the curves so I could have this little discussion. What elements X, Y, and Z, which solution curve, blue, yellow, or red, would go with the X element?
The blue one?
Good, that's right, Antonio. Because the element X decays, all right? It decays, and that's all it does is decay. What curve, red, yellow, red or yellow, what curve would go with Z, with element Z? And I saw a chat here, hold on. Hyung is correct. Yellow is Z, because that just increases. That increases. So the solution curve for element Z is the yellow curve, and you can extend T. You know, in the MATLAB code, I have T going out to 200, but you can extend it. I'm curious. Well, it's going to be good enough for your homework. We can look at it a little more. Even on Thursday, but you have enough to do your homework here. Then the red graph looks kind of red to me. Yeah, the red would be Y because it increases. Element Y gets built up based off element X, but eventually it's going to decay into Z as well. All right, how many think this is pretty cool? Pretty cool. Okay, Antonio likes it, Matthew likes it, Andre likes it. Wonderful. Wonderful. Another application of differential equations. Are there any questions? That's right, Matthew. I agree. It really is. It really is. And you can learn a little bit and adjust the graph, you know, as you see fit. But you know, you have the basics here. All right. Well, if we're good, I want to do one more example here. Then let me stop here. And half-lives you have to estimate based on the graphs. Okay. I'll let you work that out. So in the homework that's due on Thursday, there's a problem where you have to, you know, get the graphs and then estimate half-lives. So you might have to put in, like, you know, half-lives. You might have to put in, you know, try to make a very good guess, but then you might have to put in 3 or 4 guesses, you know, on that. Can everybody hear me okay?
Yeah.
Justin can.
Yes.
So Andrea, I think all right, thank you. Just gonna say log back in, Andrea. And hopefully that'll help. Okay. All right, now let me go to another example. Now this example, you're not going to have time to copy it down, okay? And I don't necessarily want you to copy it down. I want to just basically talk about this example, and then go to the solution, okay? Because there's artwork here. So here we have 3 large tanks, okay? 3 large tanks. Excellent, Andrea, excellent. 3 large tanks contain brine as shown in the figure below. All right, so again, you don't need to copy. Just you have tanks A, B, and C. And the tanks are connected to each other. And what we want to do is we want to construct a mathematical model for the number of pounds of salt, X1, X2, and X3 at time t in tanks A, B, and C, respectively. Okay, that's what we want to do. All right, one moment here. So if we look at tank A here, how many to determine, so when they say construct a mathematical model, they want, like, you know, dx dt, dy dt, and dz dt. But let's focus on dx dt. To determine the differential equation for dx dt, how many things are we going to have to consider? How many things are we going to have to consider? How many, like, looking at tank A, how many components are we going to have to worry about? How many rates are we going to have to worry about? That's right, Antonio. That's right, Ann. Well, how many? Okay, so I like what Ann said here. But how many in tank A? How many inflows are there? Good. There are 2 inflows. Good. And how many outflows are there? 1 out. So getting this differential equation is really no different than how you got a differential equation for tank problem before. It's just you have 2 incoming rates and 1 outgoing rate. So you got pure water coming in at 4 gallons per minute. You got a brine solution coming in at 2 gallons per minute. Okay. And that brine solution, that mixture will have, that's coming from tank B, right? So, you know, X2 will be involved for that mixture. And then the outgoing mixture here, 6 gallons per minute, is coming from tank A. So X1 will be involved for the concentration there. So if we go to the solution here just for dx1 dt, and I meant dx1, right? dx1 dt, okay, this is the pure water coming into the tank. So pure water, which has 0 pounds of salt per gallon, enters the tank at 4 gallons per minute. And then the mixture from tank B, tank B has 100 gallons in it, so at time t, the concentration for that mixture is x2 pounds per 100 gallon. That flows in at 2 gallons per minute. But then leaving the tank, okay, at 6 gallons per minute is the mixture from tank A. And that concentration would be x1 per 100, x1 pounds per 100 gallons. So you see, I'm still using units here. I'm still using units to kind of double check that I'm doing things right, you know, gallons simplify out, and I'm left with pounds per minute everywhere. Okay. And incidentally, why is it important for the mixture to be leaving at 6 gallons per minute? If we go back to the picture, and incidentally now this is the dxt1 dt equals x2 over 50 minus 3/50 x1. Is it important based on the picture? I mean, what do you notice about 4 gallons per minute, 2 gallons per minute coming in, and then going out is 6 gallons per minute? What do you notice about that? Why is that? Antonio had a comment. Okay, the volume doesn't change. Good. Volume remains stable. Same. So the amount of fluid going out equals the amount of fluid coming in. Okay, great. Same in, same out. That's right, Thomas. Now, for tank B, you have a similar situation. Okay, well, it's a little different, right? But you have incoming here from tank C. You have incoming mixture at 1 gallon per minute, and then you have incoming mixture from tank B at 5 gallons per minute. Wait, hold on. No. Let me rephrase that. No. For tank B, you have an incoming mixture at 1 gallon per minute, and then you have an incoming mixture from. So tank B, you have an incoming mixture from tank C at 1 gallon per minute. For tank B, you have an incoming mixture from tank A at 6 gallons per minute. Okay, and then, oh my goodness, you have two outgoing mixtures coming from tank B. Okay, that add up to 7 gallons per minute. Well, okay. So again, for dx2 dt, I didn't show in all the little steps, but I can tell you, that's right, Thomas, 7 gallons in, 7 gallons out. dx2 dt is going to equal this differential equation, and I'm going to let you, confirm that. And then finally, going back to the picture, for tank C, you have an outgoing mixture from tank C. You have two outgoing mixtures that add up to 5 gallons per minute, and then you have an incoming mixture into tank C from tank B, and then you can show that dx3 dt is going to equal that differential equation. So of course you can confirm that. And you already know how, based on dx1 dt, how to get the differential equation. Are there any questions on this particular problem? This kind of problem? All right, well, on that note, I'll stop the recording.